Good morning. So we're going to start an introduction to statistical inference. Although we're not going to get specifically into that today, we're going to set up our knowledge base so that we can talk about statistical inference. So this is some refresher content. The idea behind statistics is to make inferences about the population from sample data. So we're going to collect data from samples from the population. Samples can be of any size. That means, when I mean size, I'm talking about the number of individual units. Like we can collect data from 20 people out of a population of 350 million people. So a sample is just a set of individuals from within the population. Another refresher, let me remind you what a probability distribution function is. I talked about those previously. I used the binomial and Bernoulli as examples of probability mass functions. So both probability mass functions and probability density functions are probability distribution functions. Probability mass functions apply to discrete variables such as biological sex, a count of the number of cigarettes smoked in the past 30 days. Probability density functions apply to continuous variables such as a variable that's normally distributed, like one's weight in pounds. When we start moving on towards statistical testing, we get away from what we did last week, which was looking at a person's percentile, but it's similar. We'll start by, instead of looking at individuals and how they compare to the population, we'll look at samples and how they compare to the population. So there's a lot of similarities. We'll even do a Z conversion at some point. Not quite yet, but we'll do a Z conversion at some point that will allow us to test whether our sample is representative of the population or comes from a different population. But we have to start with this idea of a sampling distribution of the mean. We're dealing with samples now instead of individuals. So if we were to collect every possible sample of some size, n, so you'll see here I have size n, so n can be any size, 10, 20, 100, 1,000. We calculate the mean of each of those samples, and then we plot the means, as we do here in this figure, and I'll discuss this figure in a moment. We would plot a histogram of those means. And we could take the mean of that sampling distribution of means. So let me just say that again, make sure it's clear. I collect samples of some specific size, and let's just use this example. We have a population of 10,000 with a mean of 173 and a standard deviation of 30. So this is the figure right here. And we're collecting samples of size 10 from that population. So we collect every possible sample of size 10 from that population. For each of those samples, we calculate the mean. And then now we use those means as our data points and we plot those means. That plot is a sampling distribution of the mean. If we take the mean of that sampling distribution of the means, the mean of that sampling distribution would equal the population mean. The standard deviation of that sampling distribution of means we call the standard error of the mean. So here's an example where we have a variable that follows what's called the log normal distribution. Interesting that it's kind of skewed to the right. So this isn't a very non-normal distribution. It's skewed a bit to the right. You'll notice though, when we plot the sampling distribution of the mean, it's normal. Now this is a very thin normal distribution, but it is normal indeed. So here's some interesting observations about the sampling distribution of the mean. First of all, means are always unbiased estimates of the population mean. What do I mean by that? If something is biased, it's generally biased in a given direction. So for instance, if all of the values in the sample were above the population mean, we'd have a positive bias. If all the sample means were below the population mean, we'd have a negative bias. But when we collect means from the population, they can be either above or below the population mean, so we consider them being unbiased. So they're unbiased estimates of the population mean. Second, the standard error of the mean is inversely related to the sample size. It's inversely related to the sample size. So the larger the sample size, the smaller the standard error of the mean. So the larger the sample size, the thinner this distribution will get. It gets thinner and thinner and thinner. And you can see this because when we calculate, and I'm kind of going a little bit of a reverse order here, but I'll go back and make sure that you're clear on everything. The calculation of the standard error of the mean is the standard deviation divided by, and this is the population standard deviation because it's a Greek letter sigma, divided by the square root of the sample size. So the larger the sample size, the smaller the standard error of the mean. And remember, the standard error of the mean is the standard deviation of the sampling distribution of the mean. So the larger the sample size, it'll get smaller and smaller, it'll get thinner and thinner and thinner and thinner, which has implications for statistical testing, power, type 1 error, type 2 error, things that we're going to talk about later. So we talked about that. So this is falls under that rubric of square root law, right? Okay, here's another interesting one. You've noticed I mentioned that this is normal. So the standard, the sampling distribution of the mean, it is normal. Now, its normality will depend on a couple things. The sample size, the larger the sample size, the greater the tendency towards normality. And the sample size is dependent on the shape of the population distribution. So this is not a normal distribution, but it's not horribly skewed to the right. Skewedness means that there are some high values here. Skewed to the right means there's some high values, so that this distribution is being pulled out towards the positive. If there were some very low values, the distribution would be pulled to the lower ends, right? But so it's not terribly abnormal or non-normal, so we don't need a large sample size. Here the sample size is only 10 to reach normality. If we are dealing with data that are highly skewed or they're not very normal looking, we'll end up needing larger sample sizes. But the point is that the greater the sample size, we can take any distribution that has a mean, and convert it into a normal distribution. And that's pretty cool, right? We call this the central limits theorem. There's two interesting facts here. One we call the law of large numbers. So the larger the sample size, the closer the sample mean approximates the population mean. So here's an example of this. So we start with a sample size of 1 and go to sample size of 10,000, and the population mean here is somewhere between 170 and 175. You'll notice as sample size gets larger, it tends towards the population mean. That's pretty cool. That's called the law of large numbers. Central limits theorem is a little bit more robust than that. So as the sample size increases, the sampling distribution of the mean tends towards normality. And we just talked about that a moment ago. And here's an example with the normal approximation of the binomial. So the binomial is clearly not a normal distribution. However, as the sample size gets larger and larger and larger, it starts approximating normality. And there's actually a really good figure in your textbook that shows you the difference with sample sizes and how it approaches normality as the sample size gets larger. Here's a sample size of 100 versus a sample size of 10, and you see that this is much more normally distributed. All right, so let's just recap all of this to make sure it's clear. And we'll be using this more when we do statistical testing. When we collect a sample and we want to make an inference of the mean, we appeal to this sampling distribution of the mean. So we imagine that we're collecting data from every possible sample of whatever sample size we have from the population. If we take the mean of all those samples, that mean will equal the population mean. And the standard deviation of that sampling distribution of the mean is what we call the standard error of the mean. And the standard error of mean is the population standard deviation divided by the square root of the sample size. And we know from what I just mentioned prior that the larger the sample size, the smaller this standard error of the mean. So there's an inverse relation between sample size and the standard error of the mean. So that's something that's really important to know. We'll talk later about power, and power is the probability to reject a false null hypothesis. Power gets larger as we get a larger sample size. So you can see that this is going to come into play. In fact, most statistical tests that we do is some kind of estimate divided by error, and this standard error is in the denominator. So you can imagine as this value gets larger, our statistical test will get large. As n gets larger, this standard error will become smaller, so our denominator will get smaller, allowing our statistical test to increase and gives us more power to reject a false null hypothesis. We'll be discussing that next week. The sampling distribution of the mean is normal, as I mentioned, and has a mean, mu, and a standard deviation equal to the standard error. So we're dealing with the sampling distribution of the mean, not an individual value. We talked about how as the sample size gets larger, the sample means approximate the population mean. Here's this nice figure for that. And we talked about the central limits theorem, how regardless of the distribution of the population, the sampling distribution of the mean will tend towards normality as the sample size increases. Okay, let's talk about one specific case, the binomial random variable. This is one of our favorites, and we talked about this already. So the binomial random variable we know is, so this symbol is x, is the squiggly line here, or the tilde is approximately binomial, with the parameters being n and p. So n is the number of independent Bernoulli trials, and p is the probability of success for each of those independent Bernoulli trials. The mean of this distribution is n times p, and its standard deviation is square root of npq. And I showed you how as n increases, the binomial tends towards normality. So we can use that. First of all, calculating the binomial is very cumbersome, as we saw. And it would be easier if we can use a normal approximation and then appeal to one of those tables, right? Like in the back of our textbook. I think it's table 2 or table B is the z distribution, the standard normal distribution. So imagine if we can apply that table to the calculation of the binomial. It'll make our lives a lot easier. For the normal approximation of the binomial to apply, we need this quantity, which is actually the variance here, right? Because the standard deviation of the binomial is square root of npq, so the variance has to be greater than or equal to 5 to get the best approximation. If you're calculating npq and it's less than 5, you have to use the binomial to calculate the probability. So you have to give us what's called an exact probability calculation. So this is the number of successes, approximately normally distributed. So this is if npq is greater than or equal to 5, with np is the mean, and square root of npq is the standard deviation. We can also apply that to the proportion. So sometimes we deal with proportions rather than with number of successes. This is actually kind of, it looks like a totally different quantity, but it's just this quantity divided by n, because that's what a proportion is. So np divided by n is p, right? And square root of npq divided by n is pq divided by n, or the square root of that quantity. So the proportion, and we do an estimate for proportion, it's coming from sample, we have a little hat on it, is approximately normally distributed with the parameters p and square root of pq over n. So here we can see how both of them are distributed, the count of the number of successes and the proportion. They're both normally distributed. So this is an example of a normal approximation of the binomial. Okay, let's work out some problems. Let me open this up. Oops. And we'll do a set of problems from your textbook. Again, you can look these up yourself. I mean, the answers are either in your textbook or in our file, but I'll do them for you here, run you through these. These are fun, and the first one is not so much fun. Or I mean, the second one is not so much fun. So let's start here. So let's go to item 8.9, and this can be found on page 191 of your textbook. Pediatric asthma survey, n is equal to 50. Suppose that asthma affects 1 in 20 children in the population. You take this an SRS, simple random sample of 50 children from this population. Can the normal approximation of binomial be applied under these conditions? If not, what probability model can be used to describe the sampling variability of the number of asthmatics? Okay, so the question is, can we apply the normal approximation of the binomial? So the question is NPQ greater than or equal to 5? So let's see, we got simple random samples 50. Now it says 1 in 20, so how do I get that? So I just divide 1 divided by 20. So sometimes you're not going to get, so you have to understand probabilities, right, to be able to be able to make this calculation, and the language used with probabilities, right? So 1 in 20 is 1 divided by 20, which gives us 0.05, which is our p, our probability of success. 1 minus p, also sometimes it's referred to as q is equal to 1 minus p, is 0.95, because it's 1 minus 0.05 is 0.95. So is NPQ greater than 5? Well, I got 50 times, so n is 50 times 0.05 times 0.95 is 2.375, which is definitely less than 0.5, so less than 5, so we cannot use the, so your answer is no, we cannot use the normal approximation of the binomial, sadly. So which distribution should we use? We have to use a binomial. So x is approximately binomial with n equals 50, p is equal to 0.05. So that's how you'd answer that one. Now that, because of that sad answer here, you'll see that to answer the next question, we have to actually use the binomial. So the second question, 8.10, is pediatric asthma survey again. In the survey introduced in exercise 8.9, what is the probability of observing at least 5 cases in a sample? So we have 50, right? So, I mean, we could certainly add together probability x is 0 plus probability x is 1, 2, 3, all the way to 50. That would take a lot of work and a long time, and you'd hate me. Or we could do 1 minus the probability that x is less than or equal to 4, because this is asking you what's the probability that x is greater than or equal to 5. That's the same as 1 minus the probability that x is less than or equal to 4. See, I can do less than or equal here because these are discrete values. I mean, there's no 4.5, right? These are discrete values. So I have to actually go and calculate each of these. So this is good review for your binomial if you're struggling with this. So the first ones, I'm just going to calculate them. And the last one I'll do just a simple calculation. The last one I'll work it out fully just to refresh your memory. So probability that x is equal to 0, so it's 50, choose 0, which is 0.05 is your p, raised to the 0. times 0.95 raised to the 50. So this is your binomial equation applied. 50 choose 0 is 50 factorial divided by 0 factorial times, well, it's times 50 minus 0, which is 50 factorial. These two cancel out, right? And then what you get here is 1. And 0.05 to the 0 is equal to 1, so there's no value here. And the last thing we have is 0.95 raised to the 50. If we do this calculation, we get 0.0769. So that's the probability of 0 successes. And we repeat that for 1, 2, 3, and 4 successes. For 1 success is 0.202, 2 successes is 0.261, 3 successes is 0.2199. Sometimes I carry these out to 4 decimal places. I usually stop when I can't round up anymore. That's where I stop. Now for the p is equal to 4, I worked this out completely just to give you a refresher on how to do this. Okay, so when x is equal to 4, we have 50 choose 4 times the probability p is 0.05 raised to the 4. So it's always raised to whatever x is. So this is n choose x, right? N is 50, x is 4. And then the second part is n minus x, so 50 minus 4 is 46. So let's take a look at this. It's 50 factorial. So this is how we work out this binomial coefficient. So 50 choose 4 is the same as 50 factorial divided by 4 factorial times n minus x, so it's 50 minus 4 is 46 factorial, times 0.05 to the 4, 0.95 to the 4, 6. So I actually worked it all out for you. 50 factorial is the same as 50 times 49 times 48 times 47 times 46, 45, blah, 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 going all the way down to 0 factorial. However, since in the denominator we have a 46 factorial, I stop at 46 factorial in the numerator because these two will cancel out, saving us a lot of toil. So what I have left is 50 times 49 times 48 times 47 divided by 4 factorial. And then we have to just work these guys out here. So 0.05 to the 4 is this large number, or small number, excuse me. 0.95 to the 46 is this small number, right? I work this out, I get, geez, what is that? I got a large number here, 5,527,200 divided by 24. I get a very small number here. And my final probability for 4 successes out of 50 is 0.135975. Again, I carried this out further because I wanted to stop where I couldn't possibly round up anymore. So these values here give us the probability that x is less than or equal to 4. So I just have to add those up, and they add up to 0.896. 0.896. Okay? So let's finish this up. I think I can, yeah. Let's see. I can't open up that other one. Let me open up the other one. I need this one, right? There you go. All right. So let's increase that in size a little so you can see it. Okay, so what's left over? So we need the probability that x is greater than or equal to 5. So we calculated the probability that x is less than or equal to 4. So since those are complementary, either being greater than or equal to 5 or less than or equal to 4 are complementary, the probability that x is greater than or equal to 5 is 1 minus 0.896, which is 0.104. So as you can see, this is a very cumbersome calculation, and we don't want to have to do that. It's easier if we can use the normal approximation of the binomial, which we can do if NPQ is, I think I've been saying greater than or equal to 5. I should say greater than 5. So I apologize for that. Greater than 5. But, you know, they're so close to one another. I mean, you're going to be pretty close anyway. So, but let's stick with NPQs greater than 5. Okay, and I'll make sure that I don't give you anything when I test you that's right at 5. All right, so let's go to it's 8.11 Pediatric Asthma Survey. Suppose we redo the survey addressed in the prior 2 exercises now using n equals 250. Can we use the normal approximation of the binomial in this instance? What's the probability of seeing at least 25 cases in the sample. All right. So we do NPQ again, or N, and again, Q is 1 minus P. So some textbooks use Q, some use 1 minus P. Let's just go with what they have here because it's simpler. Well, NPQ is 250 times 0.05 times 0.95. We get 11.875. So this is greater than 5 for sure. So yes, we can use it, thank goodness. So we wanted to know if the number of successes in your textbook, and I showed you earlier, we can do both the probability distribution, just the probabilities themselves, or the probability of a certain number of successes, or we can do the number of successes as being normal. And here we're asking for the number of successes. So this is normally distributed. N is NP. So N is X is distributed as an approximately distributed as a normal, with its parameters NP for the mean, and its standard deviation is the square root of NPQ. We know that NP, calculating N times its probabilities, 12.5, and the square root of NPQ, well, that's just the square root of this value here. This is NPQ. It's 3.446. So this is how you'd write your distribution for X, your normal distribution. So X is approximately normal, 12.5, comma 3.446. So mean and standard deviation. If we wanted to do the proportions, the sample proportions instead, we'd say they're approximately normal, P and square root of PQ over N. So we'd write that as 0.05 because we know that's our probability of success. And square root of PQN is 0.01378. All right, question is X greater than or equal to 25? Okay. Well, since we want to convert this into a normal, and we know that we have the ability to do so, if you recall from the last chapter, converting something to a normal distribution, we can use this Z calculation, where Z is the value minus the population mean divided by the population standard deviation. So Z is the value minus the population mean divided by the population standard deviation. Our value that we're looking for is 25 successes minus our mean is 12.5, and our standard deviation is 3.446. We just calculated those. So that's 12.5 divided by 3.446, or 3.627. All right, so now we go back to our table in the back of our textbook, which is table B in the appendix on pages 542 and 543, and we need to find a value 3.627, and I'm looking at this table and it doesn't go beyond 3.4, so this value is not in the table. So what that means is that Z value is way out there, so this probability is going to be extremely small. If I look at page 543 where it says 3.4 and I work my way all the way across to 3.49, the largest probability of the table is 0.9998. So this value, or these values in the table, are everything accumulated from left to right, from the smallest value to the largest value. So this is telling us that having a Z value of 3.627 is extremely far to the right. That means that the probability that X is beyond that value is going to be very, very small. What I would do here now is I would say, what's the probability that X is less than or equal to 25? So to the left. Remember, the table gives us everything to the left of your Z value. So I look in the table and I cannot find that Z value. So at minimum, because the last value in the table in the bottom right-hand corner of page 543 is 0.9998. That means a probability of a Z value of 3.627 is going to be at least 0.9998 or 99.98. So the probability of a value less than or equal to 3.627 is at least going to be 99.98, right? So it's going to be very, very small. To find the probability of a value larger than that, I'll subtract 0.9998 from 1, and I'm going to get 0.0002. Now, since this value 3.627 is not in the table, and the value p equals 0.0002 applies to a z-value of 3.49. How I got that is I look at the left-hand column where it says z tenths, and I get 3.4, and I work my way to the right to the hundredths column that says 0.09. So the probability the probability value of 0.9998 applies to a z-value of 3.49, and since this value is larger than that, my probability is going to be smaller than 1 minus 0.9998. So that's why I put p is less than 0.0002. In your textbook, if you look at the answers, which you can look at, it's actually in the back of the text for the even numbers, for the odd numbers, excuse me, it says p is equal to 0.000. It doesn't even give you a value because it's so small. All right, we can discuss these in class. These problems, we'll work them out tonight. Okay, thank you. Have a good evening or good day.